How did everything, this universe, the galaxies, the stars, how did it all erupt from the absolute void? For millennia, we've wrestled with this question, clinging to the comforting idea that something must have been there, a seed, a spark. But what if I told you that nothing isn't what you think it is? What if nothing is the most volatile, active, pregnant state imaginable? Forget the tranquil, silent vacuum. The true cosmic void, the one physics reveals, is a seething, boiling maelstrom, a quantum foam where particles flicker into existence and vanish in the blink of an eye. It's a cosmic credit card. Constantly racking up debt, it instantly repays. But here's the secret, the mind-shattering possibility. What if one of those fleeting, ephemeral fluctuations, one of those impossible whispers in the void, didn't vanish? What if it just kept going, inflating, exploding, until it became everything we see? Can our entire universe truly be the ultimate cosmic magic trick, pulled from the hat of absolute non-existence? You see, for most of human history, when we pictured nothing, we envisioned an empty room, a cosmic vacuum, utterly desolate, silent, inert, a vast black canvas with no brushstrokes, no paint, just nothing. It's a comforting thought, isn't it? A blank slate, a perfect starting point. But prepare for a mind-bending truth, a secret the universe has been whispering to physicists for decades, a revelation that will shatter your deepest assumptions. That nothing is a lie. The cosmic void, the deepest, most barren expanse you can possibly imagine, is not empty at all. It is a seething, roiling, furious ocean of pure potential, a cosmic maelstrom that defies every ounce of our common sense intuition. This isn't your grandfather's vacuum. This isn't the silent, frigid emptiness between galaxies, the kind where a starship would drift in serene desolation. No, this is the quantum vacuum, and it is anything but quiet. Imagine, if you will, the most volatile, energetic, restless place in existence. That's the quantum vacuum. It's not a void. It's a fundamental field, an intricate, unseen fabric interwoven with every single point in space-time, humming with an unimaginable latent energy. It's the ultimate cosmic crime scene, the scene of the universe's most audacious birth. And our first crucial clue about how everything burst forth lies in understanding its bizarre, chaotic nature. Within this quantum froth, this cosmic stew, something utterly impossible is happening. Constantly, everywhere, all the time. Particles are screaming into existence, then vanishing just as quickly. We call them virtual particles. Think of them as fleeting ghosts, cosmic phantoms that don't just appear, they borrow their very existence from the vacuum itself. They materialize for an infinitesimal fraction of a second, and blink of an eye shorter than you can possibly conceive. And then they repay their energetic debt, winking out of existence before they can ever be truly observed directly. It's like a cosmic credit card with an infinite limit, but an ironclad, instant repayment clause. You can buy anything you want, a particle, an antiparticle, even a whole universe, but you must return it immediately. No exceptions. A particle-antiparticle pair, say an electron and a positron, can spontaneously erupt from the vacuum, exist for a fleeting moment, and then annihilate each other, returning the borrowed energy to the vacuum. This isn't some rare, exotic phenomenon. It's a continuous, frantic dance of creation and annihilation happening billions of times per second in every cubic centimeter of what we thought was empty space. It's the universe's ultimate zero-sum game, a constant flux where energy is borrowed and repaid, ensuring the total energy remains precisely zero. This isn't theoretical conjecture. It's a cornerstone of quantum field theory, a framework so robust it underpins nearly all of modern physics, and it's backed by staggering experimental evidence. The very forces that govern our universe, the electromagnetic force that holds atoms together, the strong and weak nuclear forces, they all arise from the incessant churning of these virtual particles, mediating interactions, giving rise to fundamental properties. The famous Casimir effect, for instance, where two uncharged metal plates in a vacuum are mysteriously pushed together by the subtle pressure of fewer virtual particles between them than outside, is a chilling, tangible proof of this seething, hidden activity. The quantum vacuum isn't just a passive container for the universe. It's an active, dynamic player. It's alive, buzzing with a furious, untamed energy that defies our common sense. It's a truth so profound, so counterintuitive, it shatters the very concept of empty space. Our universe, with all its grandeur, is founded on this wild, unstable, inherently fertile nothing. This turbulent quantum sea, forever giving birth to ephemeral whispers, is the first, most crucial piece of our cosmic detective story. It's the unstable element that holds the secret to everything. It's the nothing that refuses to be empty. It's the fertile ground from which, impossibly, everything might have sprung. So we've established that nothing is a bustling, chaotic marketplace of fleeting virtual particles, constantly popping in and out of existence, borrowing energy and repaying it instantly. But here's where the cosmic detective story truly thickens. This inherent instability, this furious, energetic churn of the quantum vacuum, isn't just a quirky side note of physics. It's the very engine that might have ignited our universe. It's the second most tantalizing clue in our quest to understand how everything emerged from the apparent void. Think of it this way: these virtual particles, these cosmic ghosts, are like tiny, spontaneous ripples on the surface of an infinitely deep, infinitely energetic ocean. Most of these ripples are insignificant. They appear, they vanish, leaving no trace. But what if just once one of these ripples, one of these quantum fluctuations, was different? What if it lasted just a tiny fraction of a second longer? What if it was infinitesimally larger than its countless brethren? This is where the profound, almost unbelievable potential of the quantum vacuum truly reveals itself. The laws of quantum mechanics, the very rulebook of the subatomic world, tell us that absolute stillness, absolute emptiness, is impossible. There is always an inherent, irreducible jitter and uncertainty. It's like trying to perfectly balance a pencil on its tip. It's fundamentally unstable. The quantum vacuum, therefore, is never truly at rest. It's always fluctuating, always vibrating, always trying out new configurations. And within these fluctuations lies the audacious possibility, the birth of an entire universe. Imagine a single microscopic quantum fluctuation, a tiny bubble of energy, a whisper of a future reality, just slightly larger, just slightly more persistent than all the others. This isn't a real particle in the conventional sense, not yet. It's still a virtual event, borrowing its existence. But what if, at a specific, unimaginably tiny point in space-time, this fluctuation didn't immediately collapse? What if, against all odds, it found a way to sustain itself, to escape the immediate repayment of its cosmic debt? This is the point where the ephemeral becomes the foundational. This is the moment where the universe, perhaps, took its first breath. This concept isn't about creating something from literally nothing, like pulling a rabbit from an empty hat. It's about harnessing the inherent instability of the quantum vacuum itself. It's about nothing that is so fundamentally pregnant with possibility, so inherently energetic, that it can, under the right conditions, spontaneously give birth to something real and lasting. It's the ultimate cosmic gamble, a moment of pure quantum audacity, where a fleeting statistical anomaly becomes a cosmic cataclysm. The evidence for this radical idea isn't direct observation of a baby universe bursting forth. We're still working on that, but rather the incredible consistency and predictive power of the theories that arise from it. Theories that explain why our universe looks the way it does, why it's so incredibly flat, why it's so uniform on large scales, and why it's filled with the very stuff that makes us up. The universe isn't just there. It carries the subtle, intricate fingerprints of its violent, quantum-driven birth. This idea challenges everything we thought we knew about creation. It suggests that the universe isn't an anomaly, but a natural, perhaps even inevitable consequence of the fundamental laws governing the quantum realm. It turns nothing from a passive absence into an active, creative force. It's a profound shift in perspective, moving from a static, empty void to a dynamic, effervescent source of all reality. If you're finding your mind stretched by these cosmic revelations, and if you're as obsessed with these secrets as I am, then smash that like button and subscribe to the channel, because we're just getting started peeling back the layers of reality. And trust me, the universe has far more astonishing secrets to reveal. We've peered into the seething heart of the quantum vacuum, that cosmic nothing buzzing with fleeting particles. We've even dared to imagine a single, audacious fluctuation refusing to vanish, clinging to existence by a thread of pure quantum chance. But how does a subatomic whisper, a microscopic bubble of borrowed energy, transform into something as gargantuan as our entire universe, spanning billions of light years and teeming with galaxies? This is where the detective story reaches its dramatic climax, where the how of creation is finally unveiled through an explosive, mind-bending process called inflation. Imagine, if you will, that tiny, persistent quantum fluctuation, that improbable bubble of reality. For a fleeting instant, perhaps a mere trillionth of a trillionth of a trillionth of a second, that's 1036 seconds, if you're counting the zeros, something extraordinary happened. This tiny region of space-time, this nascent universe, was suddenly, violently, and exponentially stretched, not just expanding, but inflating at a rate so incomprehensibly fast, it defies all earthly analogies. Think of it like this. Take a deflated balloon. Now imagine a single microscopic speck on its surface. Now inflate that balloon to the size of a planet in less time than it takes light to cross a single atom. The speck, though still microscopic in its true size, would now be separated from other specks by vast, unimaginable distances. That's the essence of cosmic inflation. It took a region smaller than an atom and blew it up to macroscopic, then truly cosmic, scales in an instant. This wasn't just the Big Bang. This was the prelude to the Big Bang, the cosmic trigger that set the stage for everything that followed. What powered this astonishing burst? The leading theory, first proposed by Alan Guth, posits that this tiny bubble contained a special kind of energy, a vacuum energy that acted like a powerful anti-gravitational force, pushing space apart at an accelerating rate. It was like a temporary, supercharged form of dark energy, but far more potent. This energy was inherent to the quantum field itself, a kind of false vacuum state that was incredibly unstable. When this false vacuum decayed or rolled down to a more stable lower energy state, it unleashed its tremendous potential energy, driving the rapid expansion of space. This isn't just a convenient handwave to explain the universe's origin. It's a brilliant strategic move, a cosmic chess game solution that elegantly resolves several long-standing paradoxes in cosmology. For decades, scientists wrestled with the flatness problem. Why is our universe so incredibly flat, so perfectly balanced between collapsing and expanding forever? Inflation explains it. Imagine inflating a tiny crumpled piece of paper to the size of a continent. From our perspective on the surface, it would appear perfectly flat, regardless of its initial curvature. The extreme stretching smooths out any initial lumps or bumps. Then there's the horizon problem. Why is the cosmic microwave background radiation, the faint echo of the Big Bang, so remarkably uniform in temperature across the entire sky, even in regions that were causally disconnected in the early universe? How could they have reached thermal equilibrium? Inflation provides the answer. Before inflation, all these regions were in causal contact, part of a tiny, uniform patch. Inflation then stretched that single uniform patch across the entire observable universe. It was like taking a perfectly mixed cup of coffee and stretching it across the entire observable universe in an instant. The uniform temperature is a fossilized memory of that initial tiny connected state. So this tiny quantum fluctuation, this whisper from nothing, found itself in a state of immense unstable energy. This energy then ignited the inflationary epoch, a period of exponential expansion that took a subatomic realm and blew it up into the vast cosmic stage we inhabit. As inflation ended, the tremendous energy stored in that false vacuum was converted into a hot, dense soup of particles and radiation, the very hot, dense state we traditionally call the Big Bang. Inflation was the spark, The Big Bang was the ensuing conflagration. It's the ultimate transformation, turning an infinitesimal, borrowed flicker of existence into the grand, fiery birth of everything. It's the ultimate visionary's gambit, played by the universe itself, an audacious bet against the odds that paid off spectacularly. We've traced the universe's audacious journey from a seething quantum nothing to the explosive inflationary burst. But how do we know any of this isn't just a brilliant, unhinged theoretical fantasy? This is where our cosmic detective story yields its most compelling evidence. The undeniable fingerprints left behind by inflation itself, the subtle, yet profound patterns imprinted on the very fabric of the universe's earliest light. Enter the cosmic microwave background, or CMB. If the universe has a baby picture, this is it. It's the oldest light we can detect, a faint glow permeating the entire sky, a relic from about 380,000 years after the Big Bang. Before this time, the universe was a superheated, opaque plasma, too dense for light to travel freely. But as it expanded and cooled, electrons and protons finally combined to form neutral hydrogen atoms, and suddenly the universe became transparent. The light that was scattering everywhere was finally free to stream across the cosmos. We see that light today, stretched and cooled by billions of years of cosmic expansion as microwaves. Now, if the universe had simply started as a uniform, perfectly smooth Big Bang, the CMB would be a perfectly uniform glow across the entire sky. But when cosmologists looked at it with unprecedented precision, first with COBE, then WMAP, and most recently with the Planck satellite, they discovered something extraordinary: tiny, almost imperceptible temperature fluctuations. These aren't random splotches, they are specific statistical variations, minute, hot and cold spots that differ by only about 1 part in 100,000. These aren't just noise. They are the most profound clues in our cosmic investigation. Why are these tiny fluctuations so crucial? Because they are the direct echoes, the fossilized remnants of those initial quantum fluctuations that sparked inflation. Remember that tiny subatomic bubble that inflated? Well, it wasn't perfectly smooth. Quantum mechanics, by its very nature, dictates that there are always inherent, irreducible jitters and uncertainties. So, when that subatomic region inflated, those infinitesimally tiny quantum jitters were stretched along with it, becoming the seeds for all cosmic structure. The slightly denser regions, the hotter spots in the CMB, would eventually pull in more matter through gravity, growing into galaxies, galaxy clusters, and the vast cosmic web we observe today. The slightly less dense regions, the colder spots, would become the voids. The incredible triumph of inflationary theory is that it predicts the precise statistical properties of these fluctuations. It predicts their amplitude, their distribution, and their scale invariance, meaning these fluctuations exist on all scales, from the smallest observable patches to the largest. And the observations from the CMB, particularly from the Planck satellite, match these predictions with astonishing accuracy. It's like finding a single, unique fingerprint at a crime scene and then finding that same fingerprint on every single piece of evidence. The case for inflation, and thus for a universe born from the quantum instability of nothing, becomes overwhelmingly compelling. The CMB is our ultimate photograph of the infant universe, and it screams the story of inflation. It tells us that the universe didn't begin as a perfectly smooth, featureless expanse. It began with the subtle quantum-driven imperfections that were stretched to cosmic scales, providing the initial scaffolding for everything we see. It's the ultimate validation that the universe's beginning was not a static, perfect void, but a dynamic, inherently unstable quantum field that, through inflation, birthed the very stage on which cosmic evolution would play out. These tiny ripples are the direct, tangible proof that our universe is a magnificent, improbable outcome of nothing being far more potent than we ever dared to imagine. And so, our cosmic detective story culminates in a truth more profound and unsettling than any ancient myth. The universe, with its billions of galaxies, its unfathomable structures, and the very consciousness that contemplates it, may not have needed a something to begin. It could be a natural, even inevitable consequence of nothing being inherently unstable, a seething quantum foam pregnant with possibility. We are left with a universe that appears to have created itself, not from a miraculous spark, but from the relentless, chaotic dance of virtual particles and the explosive power of cosmic inflation. The vacuum, once thought to be empty, is revealed as the ultimate fertile ground, a dynamic source that continuously whispers new realities into existence. This isn't just a scientific theory, it's a philosophical revolution, hinting that existence itself might be the default state, a natural outgrowth of the fundamental laws of reality. The universe didn't just happen, it erupted from the fertile instability of the void, a cosmic magic trick pulled off by the very fabric of space-time itself. The quest to understand our origins continues, pushing the boundaries of human knowledge into realms once reserved for gods and poets. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.